Hi everyone. In this video, we'll discuss integer linear programming model and how to formulate them. Integer linear programming models are linear programs with the additional requirement that one or more variables must be integer. If all variables must be integer, we have an all integer linear program. If some but not all variables must be integer, we have a mixed integer linear program. In many applications of integer linear programming, one or more integer variables are required to equal either 0 or 1. Such variables are called 0, 1, or binary variables. Integer variables, especially 0 or 1 variables, provide substantial modeling flexibility. As a result, the number of applications that can be addressed with linear programming methodology is expanded. In this video, we'll discuss the example of a distribution system design on page 329. This example can be adjusted to become a transportation problem or an airline schedule problem. Basically, the Martin Beck Company operates a plant in St. Louis with an annual capacity of 30,000 units. Product is shipped to regional distribution centers located in Boston, Atlanta, and Houston. Due to the increase in demand, the company plans to increase capacity by opening a new plant in one of the following cities: Detroit, Toledo, Denver, or Kansas City. The example in the book assumes the company can use more than one city, but I change this assumption a little bit, assuming that the company only chooses to open one new plant, and I will show you how to handle this constraint. The estimated annual fixed cost and the annual capacity for the four proposed plants are shown in this table. The company also made forecasts of the annual demand at three distribution centers, as we see in the next table. The shipping cost per unit from each plant to each distribution center is presented in table 7.2. Figure 7.7 shows a network representation of the potential distribution system. This is a similar network as we see in the transportation problem in chapter 6. Basically, on the left-hand side, we have the manufacturing plants in 5 cities represented by nodes. Note that St. Louis is a current plant and other 4 present potential new plants. The number next to each node is a manufacturing capacity. For example, the capacity of Detroit plants is 10,000 units, and so on. On the right-hand side, we have distribution centers in Boston, Atlanta, and Houston, also represented by nodes. The number next to each distribution center is its annual demand. For example, the demand for Boston Center is 30,000 units, and so on. Each arc represents a shipping route from a plant to a distribution center. The number of the arc shows the shipping cost per unit for that shipping route. For example, it costs $5 to ship one unit from Detroit to Boston, and so on. Again, in this example, we assume that the company plans to open only one new plant. To formulate the linear programming model, we use the same process as before. We will write out three major components of the model first: decision variables, objective function, and constraints. Since the decision involves choosing one city or not, using binary decision variables with 0 and 1 is the best choice. Let's define decision variables. We call y1 equals 1 if a plant is constructed and destroyed, 0 if not selected. Similarly, we call y2 equals 1 if a plant is constructed in Toledo, and 0 if not. Y3 equals 1 if a plant is constructed in Denver, and 0 if not. And Y4 equals 1 if a plant is constructed in Kansas City, and 0 if it's not selected. That would help us make the decision. If the solution shows a value of 1, then we select the city. Otherwise, we do not select the city if it has a value of 0. To transportation problems, we need to have another set of variables involving the number of units shipped from each plant to each distribution center. So we call X11 is number of units in thousands shipped from Detroit to Boston as we see in the network. Similarly, we call X12 is the number of units in thousands shipped from Detroit to Atlanta, and so on. I will not list all of them. The textbook shows how to use the general form to save space. The final variable is X53 equals number of units, thousands, shipped from St. Louis to Houston. Those are decision variables. Now let's develop the objective function. The objective is to minimize the total cost, which includes shipping costs and fixed costs. The shipping costs are to ship items from plants to distribution centers, and the fixed costs are related to costs to open the new manufacturing plant. The total shipping costs are determined the same way we see in chapter 6. Basically, we multiply the shipping cost per unit by the number of units. For example, we have the shipping cost to ship units from Detroit to Boston is 5 times X11. Use the same logic for each route. We'll have the total shipping cost expression as 5 times X11 plus 2 times X12 plus 3 times X13 plus 4 times X21 plus 3 times X22 plus 4 times X23 plus 9 times X31 plus 7 times X32 plus 5 times X33 plus 10 times X41 plus 4 times X42 plus 2 times X43 plus 8 times X51 plus 4 times X52 plus 3 times X53. The fixed costs are different. The fixed cost only incurs if we choose the city. So we need to use our binary variables for this purpose. For example, if we choose Detroit, then the fixed cost for this plant would be $175,000. But if we do not choose Detroit, this fixed cost for Detroit would be 0. To formulate it, we just multiply the fixed cost of 175,000 by Y1. If we choose Detroit, then Y1 equals 1, then the fixed cost would be 175,000. Otherwise, Y1 equals 0 and the fixed cost would be 0. Using the same logic, we have the total fixed cost expression as 175 times Y1 plus 300 times Y2 plus 375 times Y3 plus 500 times Y4. That is how to use binary variables in this type of decision. Now we need to combine the shipping cost and the fixed cost expressions in the objective function. We should copy and paste the expressions over here and add min at the beginning and add plus sign here. Next, we need to formulate constraints. First, we have constraints for capacity of the plants. For example, the capacity for Detroit plant is 10,000 units. That means we cannot ship more than 10,000 units out of Detroit. The number of units shipped out of Detroit are expressed by X11, X12, and X13 as we did before. So we have the constraint for Detroit capacity as X11 plus X12 plus X13 less than or equal 10. But note that this is only true if we select Detroit. If we do not select Detroit, the capacity should be 0. To formulate that, we use the binary variable y1. So we have our constraint as x11 plus x12 plus x13 less than or equals to 10 times y1. Using the same logic, we have the constraint for Toledo capacity as x21 plus x22 plus x23 less than or equals to 20 times y2. Then we have the constraint for Denver capacity as x31 plus x32 plus x33 less than or equals to 30 times y3. And we have the constraint for Kansas City capacity as x41 plus x42 plus x43 less than or equals to 40 times y4. Finally, we have the constraint for St. Louis capacity as x51 plus x52 plus x53 less than or equals to 30. Note that because a plant already exists in St. Louis, we do not use a binary variable for this plant. Next, we'll need another set of constraints for demand at 3 distribution centers. For example, the demand at Boston distribution center is 30,000 units. That means total number of units shipped to Boston must equal 30,000 units to meet the demand. The number of units shipped to Boston are expressed as x11, x21, x31, x41, and x51 as presented before. So we have the Boston demand constraint as x11 plus x21 plus x31 plus x41 plus x51 equals 30. Similarly, we have the Atlanta demand constraint as x12 plus x22 plus x32 plus x42 plus x52 equals 20. Finally, we have the Houston demand constraint as x13 plus x23 plus x33 plus x43 plus x53 equals 20. As stated before, in this example, we assume that the company plans to open only one new plant. That means only one of 4 cities will be selected. To formulate this constraint, we set y1 plus y2 plus y3 plus y4 equals 1. Since these are binary variables with 0 or 1, this constraint will ensure that only one variable will have a value of 1 and the remaining variables will be 0. This is the difference between this video and the example in the book. To have the model in a standard math form, I will delete all explaining text and only keep the objective function and the constraint expressions. At the end, we also add constraints to ensure that variables from x11 to x53 are non-negative. We can write it in a general form as xij greater than or equals 0. Another important set of constraints is that y1, y2, y3, and y4 equal 0 or 1. And here is the entire model for integer linear programming. That is how to formulate an integer linear programming model. Thank you and bye now.